And it gets so quiet.
Yeah, everybody goes, "Oh my God, we're live now."
I don't want to say anything.
We're in space. They can't hear you, Terry.
Yeah, they can't hear you scream. They can't. Yeah. How do they know you can't? I don't know.
You know, I've seen Orion go by quite a few times now. I think I like this loop.
You like the loop?
Except it's winter time.
Mm-hmm.
It's coming.
Yes, it is. I can't believe Christmas is what? Just a little over a month away.
Yeah.
And Christmas was already in the stores 2 months ago.
Yeah.
It was. In August, yeah.
Yeah.
But it seems like we were just at Alcon. You know, it doesn't seem like it's been that long ago.
That's because it was not that long ago.
I know. But 2023 is coming up, and before we know it, it's going to be here.
Yeah.
The whole pandemic kind of completely distorted our sense of passage of time, right?
Yeah.
Yeah.
It just still doesn't feel normal. It's all moving at weird speeds. Yeah.
Yeah.
Yep. It seems like everything's kind of changed a little bit, you know?
Mm-hmm. Our perceptions, at least, right? Yeah.
Yeah, definitely.
Yeah, they keep talking about the new normal, but I don't know.
None of it feels normal yet, right?
None of it's normal. Exactly.
Just when
Not
we
at
figured
all.
out a normal, then it all changes up to something else. So
Yeah,
That's right. Constantly changing.
Yeah.
which is apparently good for our neurons as we get older. So
That's right. And that's the reason why you need to be taking lion's mane powder.
I guess I'm just going to have to do some
I am going to do
I can see Scott showing up with
a little commercial blurb for the Lion's Mane
I hope
Society.
they're sponsoring, right?
That's right. That's right.
I can see him walking.
The
in
American
the
Lion's Mane Association. Yes. Mm-hmm.
He'll have his lion mane on.
That's right. My whole suit.
Oh yeah, I look like the Wizard of Oz.
So what did you guys think of David Eicher dressed up for the Halloween thing
That
for
was
the
a
last
scream.
in the last show? It's kind of scary, you know.
It was amazing. I about
It was.
died because I opened.
And like blood dribbling out of the side of his mouth.
Yeah.
I don't know what kind of blood it was, but
Last year, I did a public lecture on Halloween for Whipple Observatory. So I wore my Star Trek uniform. So it was perfect.
well, that's cool. That's cool. Have you, Shane? Have you ever been to a Star Trek convention?
I have. I've
And
been
so,
to many.
what is that like? What is it like?
Well,
when
you know, I haven't been for maybe a decade or more, but you know, it's kind of awesome because everyone's kind of into it, right? So
right?
kind of meet the whole spectrum of people, and you kind of all love the same thing. It's kind of like being at a star party, right? Everyone just loves the same stuff, and we talk about the same stuff, and it's fun to
Right.
hang out with people who are like you are, right?
That's cool. That's cool.
Hi,
I went
gentlemen.
to
Good to see you.
I went to
Come
one in
on, Goss.
Kentucky, and I walked in the restroom, and there were two Klingon women brushing their hair. And I kid you not, I went, whoa. And they looked at me and said, haven't you ever seen a Klingon?
Primping.
It's like, wow, they really looked great.
Must have been
Did
the
they?
Goss sisters.
That's right.
We're going to share to the Austin Astronomical Society. That's a great group. Austin.
Yep.
They're a league club, aren't they?
Yes,
Mm-hmm.
and I think they're a fairly large club too.
yeah, they're
I think you're right.
a few hundred, I think.
And the Dunfermline Astronomical Society. So here we go. Hopefully I'm not messing that up.
If if we're lucky, our power won't go out. We're on the receiving end of the storm that's coming through.
At the end of 2017, a galaxy 236 million light-years away began a rare and dramatic transformation. It's an event astronomers are still puzzling over, one set off by changes near its central black hole. They first explained this as a tidal disruption event. That's when a star wanders so close to a supermassive black hole that it's torn apart. A new study of observations spanning the entire event suggests a different cause. The trigger may have been a flip in the magnetic field in the disk of material around the black hole. The sun's magnetic field reverses polarity every 11 years. On longer timescales, even Earth's magnetic field flips. Starting in December 2017, the galaxy began to brighten in visible and ultraviolet light. The source of this brightening appeared to be the disk of material around the supermassive black hole at the galaxy's center. It peaked 3 months later at nearly 100 times its previous brightness. That's when regular monitoring with NASA's SWIFT satellite began. As the visible and UV brightened, X-rays from the galaxy dimmed. By August 2018, the higher energy X-rays had disappeared completely. A few months later, the high-energy X-rays came back, even brighter than before. They returned to normal within a year. These X-rays come from a cloud of super-hot particles near the black hole. It's a feature called the corona, which is formed by the strong magnetic field. The lack of higher-energy X-rays means that this structure was essentially gone. Based on observations from SWIFT, Europe's XMM satellite, and ground-based optical and radio telescopes, here's what may have happened. The visible and UV flare results when the flow of matter into the black hole increases. This may have started when the magnetic field in the disk's outer regions began to flip. The weakened magnetic field can no longer support the corona, which vanishes. The flipped magnetic field gains strength, restoring the X-ray corona, but the inward flow of matter is still high, so this emission is stronger than it was before the flare. Finally, the corona and disk return to their states before the flare, now with a flipped magnetic field. Rapid changes in UV and visible light have only been observed in a few dozen active galaxies like this one. But this is the first time X-rays have been seen to drop out as other wavelengths brighten. These surprising events offer a tantalizing glimpse at the extreme forces at work near an actively feeding supermassive black hole.
Well, hello everyone. This is Scott Roberts from Explore Scientific and the Explore Alliance, and we are coming up on our 22nd Astronomical League live program. With me tonight is, of course, Terry Mann. Terry is the host of Astronomical League Live. She brings on the top officers from the Astronomical League, and we've got Carroll Iorg and John Goss with us also here tonight, and we've got David Levy and myself that have also been invited here. And the keynote speaker tonight is Dr. Shane Larson, who did the very first Astronomical League live program. So I'm going to turn this over to Terry and let her introduce everyone and get this thing going.
Thank you very much, Scott. I appreciate it. It's so good to see everybody again and be online. It seems like it's been a long time, and yet everything seems to be going by a lot faster than normal too. So thank you all for attending, and thank you all for viewing. We appreciate you being there for our Friday night astronomy. So how about if we start off with David Levy? David, it's always a pleasure to see you here, and you have been on just about every show we've ever done. So thank you very much for that. And how about if you get us started?
Well, thank you so much, Terry. It's really good to be here tonight. And wasn't that a wonderful eclipse? I think a lot of us had clear or partially clear sky that we were able to see this beautiful, beautiful event. It was pretty dark. I got it as an L2 eclipse. It wasn't the darkest eclipse I've seen. That one would have been December the 30th, 1963, when the luminosity was absolutely zero. The moon simply vanished in totality on that darker than ever eclipse. And so for my poetry tonight, I'm going to quote from Thomas Hardy's beautiful poem, At a Lunar Eclipse. He wrote it in 1903 after seeing an eclipse in London in 1902. And the interesting thing about it is that he's comparing the beauty, the magnificence of a celestial event to the troubles that we have on the planet Earth. And I can find no better time that it would be more appropriate than now, with the war going still on in Ukraine and a lot of uncertainty in the world right now, with COVID still going on. And by the way, having lost 2 close friends to COVID in the last couple of months, I'd like to suggest that you also remain very, very cautious about that. Anyway, here is Thomas Hardy at a lunar eclipse. Thy shadow, earth, from pole to central sea, now steals along the moon's meek shine, in even monochrome and curving line of imperturbable serenity. How shall I link such sun-cast symmetry with the torn, troubled form I know as thine? That profile, placid as a brow divine, with continents of moil and misery. And can immense mortality but throw so small a shade, and heaven's high human scheme be hemmed within the coasts yon arc implies? Is such the stellar gauge of earthly show, nation at war with nation, brains that teem, heroes and women fairer than the skies? Thank you very much, and back to you, Terry.
Terry, you are muted. There we go.
Yep. We really appreciate you being here, and thank you again. That was so nice. It's a great start to a Friday night, if you ask me. So how about Carroll, if you kind of update us on what's going on in the league here lately?
A little bit. And David, thanks so much for sharing your poetry with us. And I would like to say I saw the eclipse. I did not. We were clouded out. But your verse made it come alive. And I can imagine what it was like if I had never seen one before. So thank you. To start out with, on behalf of the 22,000 members of the league, I would like to wish the veterans among our ranks a big thank you for your service to our country. And we really appreciate all you've done to keep our freedom alive in the United States. Beyond that, we've got quite a bit going on right now. We have as Terry was saying earlier, we've put 2022 to rest as far as Alcon. Now we're getting ready for Alcon 2023, and we're very honored to have 2 keynote speakers for Alcon 2023 in Baton Rouge. First one is David Levy, editor of Astronomy Magazine, and the other one is Fred Espenek, well-known eclipse chaser and the authority on all things eclipse. So we'll have more information about that just a little bit later. The other thing that is very good to hear is that throughout all these various weather conditions in the Midwest here, for example, where I live, we have very few decent skies this time of the year. I was in Minneapolis a couple of weeks ago. Actually, it's been a little longer now. It's been about 4 weeks ago, but time goes fast. Anyway, we had an astronomy day up there. I helped them celebrate an astronomy day. And that's one of the rarities in the league. And I'd like to remind everyone of this. We have 2 astronomy days, one in the spring and one in the fall. But we get a lot more entries from the one in the spring. However, they did an excellent job of putting on that autumn astronomy day in Minneapolis. And you'll see more about that in the next reflection. Also, we are continuing to have good reports about people still out observing, even with less than ideal weather conditions. So we're always thankful to hear that. I know our friends in Arizona, in David's part of the world, you can be more selective about when you want to observe if you choose to. Here in the Midwest, we have to take what we can get, and it isn't always super good. But I'm glad to see that we're continuing to observe as our group really is out there under the skies. That's about it for right now. We will have some major announcements coming up around the first of the year, but I'm not going to tip my hand right now because I've known when one sets deadlines, sometimes you have to take them back. So I'm not going to say any more about that right now, but more will be revealed.
Okay. Thank you, Carol. We appreciate that. It seems like there's always something going on somewhere, and we all seem to be busy doing different things for different offices. So I look forward. I know some of the stuff that's going on, but I won't tip my hat either. I don't know everything. So thank you very much. I appreciate you being here too. And what I would like to do next is to ask the questions for tonight. And naturally, I'm right at the end of my slideshow here. So we're going to go up to the top. And you can kind of see what's coming up next. So tonight, I'm going to ask the 3 questions. And as you know, we will select 3 winners from these questions that are asked. But what we need to do, it's not like the Global Star Party. Tonight, we will announce the winners right after the main speakers. So please, when I ask the questions, if you could get them in within 20 minutes to a half hour, because I will give the winners' names after Shane gets done speaking. And please send your answers to secretary@astroleague.org. And as you can see tonight, 3 winners will win the Astronomical League travel mug. And we still are not doing international shipping. We still are trying to work all of that out. So as I just told you, and the winners, somebody from the Astronomical League office will be contacting the winners within the next few days. So questions for tonight. While driving on the moon, the fender on the rover was damaged. What did the Apollo 17 crew do to fix this fender? How did they fix the fender on Apollo 17's rover? And again, send those answers to secretary@astroleague.org. And you'll notice I'm going to go slow. We had 2 more people contact us and say we're going through the questions too quickly. So please slow down. So that's what we're going to do a little bit tonight. On December 7th, what part of the U.S., on December 7th, part of the U.S. will see this occultation? What planet will be occultated? What planet will be part of the occultation? So December 7th, part of the U.S. will see this occultation of what planet? And again, send your answers to secretary@astroleague.org. And the last question. On November 16th, 2022, Mars will be in what constellation? So on November 16th, 2022, Mars will be in what constellation? And again, please send your answers as quickly as you can to secretary@astroleague.org. And next up, John, get warmed up because I am headed your way. So for those of you that don't know John Goss is the one that does these fantastic announcements for AL Live. He does a great job, and I really do appreciate it. I know it has to take quite a bit of time, but he's always there and always willing to do it. So thank you very much. And he is also our media officer for the Astronomical League. So John, I will be quiet and let you talk.
All righty. I'm not muted, am I? For once. Okay. There we go. Good. It's good to be on, and thank you for having me. Thank you for inviting me. I like to come on every now and then and say a few words, and this time I will. I have a presentation to give, but I'm going to start out with something else first. And as you can see, this has nothing to do with the presentation. It's just an icebreaker. Let's see what we can do. See how much ice I can break. Okay. Now here's your test. This is not part of the 3 questions, so don't get confused on this. This is me being a wise guy. Okay, so what do we have here? Image of a sunspot, a negative image of a globular cluster, or a section of a decaying banana peel. Now, I bring this up because I had this posted on the League website, and we had the most responses ever of anything on there. It's such a silly thing. Yeah. So what is it? Well, I recently completed the globular cluster observing program. So the next morning, I'm all about globular clusters. Next morning, I'm eating my Cheerios, slicing the little banana onto the Cheerios, tossed the peel down, and I looked down and I said, I don't believe it. This is a globular cluster right in front of me, a whole bunch of them. So just think about that. The signs of the cosmos are all around you all the time. You just got to look carefully enough. Okay, enough of that. Now let's really get into this. I wanted to talk about something which I just laughingly called Astro Devo, which you might remember the band Devo from the 1980s. And they talked about devolution instead of evolution. So I thought, okay, I'm going to talk about my devolution in astronomy. Our hobby is such that we never know where it's going to lead. If you have other hobbies, at least you know what you're going to be doing. But with ours, from night to night, year to year, as we progress in it, we never really know where we're going or where we're going to end up. And I always like to tell people, the journey is just as important as the destination. And oftentimes, or every time, it's just as rewarding because you never really know what's going to come up around the bend. So we're going to look into our crystal ball here. I happen to have one at home, which I consult all too often, I'm afraid. But we're going to be looking at a few things on this idea. Like most amateurs, I started out small telescope. And as time went on, I got bigger and bigger telescopes. I started out with a 6-inch dynoscope way back in 1969, something like that. And then kind of moved up as time went on. Now, my largest telescope now is a 17.5-inch Dobsonian, which I like. Works great. But you're going to kind of hear me put things down about some of these things, but I'm not really. You do some observing. You get out under the stars. As I was saying, you never really know where your journey is going to take you. Let's just take an example here. The Open Cluster M46. I assume a lot of you have seen it. It's a nice looking cluster in the winter sky in Canis Major. Obviously, it's a Messier cluster. But, the first time you see it, you might not be expecting everything that you're actually going to end up with in the eyepiece. So you zoom in there and you're going to see have your nice cluster of, I think it's about 300-400 stars in there, actually. You got M46, but you end up with a bonus, the NGC 2438. Now, first time you see this, and if you're not aware of what you're going to be finding, you're going to look at that and go, what is that? I discovered something, but a lot of people have seen it, and it is pretty cool. So that's one illustration there of seeing something that you're going to be surprised with and enjoying the journey along the way. Okay, so you're into the hobby now. You're seeing clusters like this, dimmer ones and ones further away. You're always looking for the dimmer and dimmer objects, which can become an obsession. Now, I use obsession because of the telescope people, but a little play on words for you. So one night with my 17.5-inch, I was going through the Herschel 2 catalog, trying to earn my Herschel 2 pin from the Astronomical League, having already seen 400 objects in the Herschel list. Now I'm tapping the 400 in the Herschel 2, so I'm getting kind of up to here as far as dim stuff go, dim galaxies. But anyway, I came across this. I did a quick drawing of it. I inadvertently stumbled across M106. I didn't realize what I was looking at first, and I thought, that looks just like M31. What's it? Obviously, it can't be M31. It's wrong time of year, wrong part of the sky, and all that. So I thought, well, here's my 17.5-inch telescope. Looking at this, looks pretty good. So I also had a 4.5-inch reflector looking at M31. And I'm flicking back and forth, and I'm thinking, gosh, these two sure look very, very similar in a way. And it kind of dawned on me that here I am with big 17.5-inch, trying to get dimmer and dimmer and dimmer to make objects look like they would through a much smaller scope. So I started thinking about this. This would be my devolution realization, that perhaps I was becoming just too fed up with all these other dim galaxies in the Herschel 2 and the ARP and the Herschel 1 and on and on and on. So, I thought, well, if M106 looks pretty good in a big scope, looks like M31 in a small scope, then why do you really need to proceed to larger and larger telescopes to see dimmer and dimmer things? Because they're just going to look a little bit brighter and a little bit bigger otherwise. So if I want to see dim objects, I can stay with an easy to use small scope. Now I like putting that sentence in there because right now these telescopes are, I don't know how they're doing it, but they're getting heavier and heavier every year. And it'd be nice to have a smaller scope sometimes. Now I'm going to back off this for a little bit and circle back on this. In about 2003, members of my astronomy club, we live in Roanoke, Virginia, decided to pick out a galaxy cluster that we could designate the Big Lick cluster, because that's the nickname of Roanoke, Virginia. Long story, I won't go into it. But okay. So we picked out a cluster called Hickson Galaxy Group number 68, which happens to pass right overhead in the spring skies at about 38 degrees latitude or 38 degrees declination, and because we're at 38 degrees latitude. So we decided to start calling it the Big Lick cluster. So that then about 9 years later, this is not a big deal. It's not something you think about all the time. So 9 years later, I happen to receive a copy of the journal of the RS. And okay, well, on the back cover though was a picture taken by one of their members of the Big Lick cluster. I nearly fell over when I saw this because we just kind of did it as a humorous little thing to do, and we got the Big Lick cluster. So let's look at this a little bit more carefully.
That is beautiful.
Well, it's not my picture. If it was my picture, it would look horrible. But yes, Scott, the images are very appealing. But what do you really see through a large or small telescope when you look at clusters like this, galaxies like this? Well, here's my view through the 17.5 when I jotted everything down really quickly. There are half a dozen galaxies in there. Some are on the bright side, some are on the dim side, and I started thinking in relationship to this devolution bit. How big of a telescope do you really need to see this stuff? So what did I do? I made a mask for the front of the 17.5-inch, stopping it down various amounts, and we're going to go through that. I made a 11.25-inch mask. Now, the reason why I ended up with this is simply because that reduces the magnitude, the limiting magnitude by 1. So everything's a little bit dimmer. You can still see a number of the galaxies, but they're starting to disappear on us. Did it again, same idea. Now to a 7-inch mask, which is again dropped the magnitude by another, the limiting magnitude by full amount, and fewer galaxies. Things are getting dimmer. And I thought, well, a 4-inch telescope isn't very big. Could you see something? Could you see any one of these dim galaxies? So I put on the 4.25-inch mask, and yeah, you can still see 2 dim galaxies there with a So theoretically, if you had a small telescope, 4.25 inch telescope, you should be able to see two of these galaxies. So instead of turning around and getting that 17.5 and then buying a 20 and then a 24 and however big they are nowadays, I started thinking, well, I can still see galaxies with a really small telescope. Don't know. Started doing other things. I won't go through with everything I did. The NGC 188, which I believe is the most northern open cluster in the sky. It's not extremely easy to see. As you can see, the image on the left is with a 3-inch mask on my 10-inch telescope. So it's like using a 3-inch telescope. All I get is some fuzzy blobs. But when I go through the full aperture of that 10-inch, it's pretty easy to see. So yeah, it's kind of interesting to see what you can actually spot, what you can discern with the smaller you go instead of the bigger you go. Try to go smaller. You can see what's going on or not going on. Okay, another thing that came up to mind was location. It's where you are observing makes a big difference. NGC 7789 is in Cassiopeia. It's a really, really pretty cluster. If you have too small of a scope, you aren't going to get anything out of it. But this was, I drew this with my 10-inch telescope, and you can kind of see, well, you can see many dim stars in this cluster. So that's one time when you've got to have a larger telescope to see it. But if I use this with my 17.5, it may just be too much, and you won't have that stardust effect, the hazy glow in the background stardust effect. So aperture does play a big role in this. Another one which I did this month, NGC 55. It's in a way, I think it would be a showpiece galaxy, except for our area in Virginia, it never rises very high. So it's never far above the horizon, so it's tough to see. And it's a big galaxy. It's like 30 arc minutes across. But you can just barely see it with a 10-inch telescope. Okay. With a 4-inch, you're not going to be able to see this. One more. Okay. 8-inch telescope. I think my second or third slide, I showed all my fancy telescopes I got. I have an 8-inch f5, which I was lucky enough to take to Chile and do observing there. And M83, it's a great spiral galaxy. I think it's like 80 degrees altitude from Chile. From where I live, no. So I could actually see the spiral nature, and I was really thrilled, really thrilled with that. Now you may have noticed I have a lot of drawings in here because I really want to promote the Astronomical League sketching program. Astrophotographs are great, but astrophotographs are something that you're not really going to see. What you're going to see is something going to be, I don't want to say disappointing, but if that's what you're expecting to see, yeah, you're going to be disappointed. But you're going to see how things truly appear through an eyepiece with your own eyes. And you use sketching to try to capture this. I always found that to be very, 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 very good. And I'm going to leave you with one more instance here. We've all looked at the double cluster in Perseus. It's really pretty. You have a big telescope and look, no, it's going to be spread out way too much. You aren't going to appreciate the cluster effect of it, the diamonds on the black velvet. So with a 4.5-inch or maybe slightly larger, you're going to see a really nice looking subject there in the sky. So here we are looking at the stars. You go out on the stars in your career, in your astronomy career, you're always going to want something bigger. You're going to want something bigger, and you're going to want something bigger. And then you just might realize, that the dimmer objects in large telescopes look like the brighter objects in small telescope. So why would you want to spend all your time on that large telescope where you can haul out that little one and see this really great stuff? And sketching, not imaging, records what you really see. So the next time you go out, try to keep these perspectives in mind, that some objects you certainly got to have a big telescope, but not all of them. You can really appreciate the heavens with the small stuff. I'd say 80% of my time outside, I really just have a pair of binoculars or my smallest telescope with me. I find it enjoyable. It's not so stressful. It's just a lot of fun. So on that happy note, I'll turn things back over to Terry, and we can get this show on the road. Thank you, Terry.
Well, thank you, John. That is really, I like seeing all the drawings. I cannot draw. So, as far as if I was doing a program, I think I'm like a lot of people. I get kind of, I can't really draw. If I drew a circle, you might be able to tell it's a circle, but I'm really not an artist in that sense. So, but it is interesting to see it because I've seen some excellent drawings from a lot of people that do sketching on all the different programs. So thank you. It's nice to see that. And it's nice to know you don't have to be an artist actually to do this. Even if you can't draw, do the best you can.
Well, just remember to tell everybody that it's supposed to look like that.
There you go. Because most people probably would look like mine would look. So, okay. Well, thank you very much, John. Appreciate you being here.
Thank you.
All right. Shane, we're actually going to go to you pretty quickly here. So let me do an introduction to who Shane is. As Scott mentioned, Shane did our very first Astronomical League Live. He was our very first speaker, and he is an excellent speaker, so I wanted to have him back. We haven't seen him in a long time. That was on December 5th of 2020 that you were our first one.
I had not remembered that. So
yeah.
Thanks for having me back.
That long.
Yeah.
So I wanted to have you back again, and we do appreciate you being back so much. So Shane Larson is a research associate professor of physics at Northwestern University, where he is the associate director of Sierra, Center of Interdisciplinary Exploration and Research in Astrophysics. He works in the field of gravitational wave astrophysics, specializing in the studies of compact stars, binaries, and galaxies. He works in gravitational wave astronomy with both ground-based LIGO ground-based LIGO project and the Future Space-Based Observatory LISA. He was formerly a tenured associate professor of physics at the Utah State University. He is an award-winning teacher and a fellow of the American Physical Society. He's an avid amateur astronomer. I can vouch for that. Greenback, you do some amazing stuff. He is an avid amateur astronomer, observing with two homemade Dobsonians, a 12.5-inch named Equinox, and a 22-inch named Cosmos Mariner. He contributes regularly to public science blog at writesciencewordpress.com and tweets with the handle at Space Jedi. Star Wars. I was going to say, we were talking about Star Trek. There's Star Wars. I love the title of his talk. It is Monsters in the Cosmic Sea, Black Hole Tales from the Edge of Space. That is so cool. So Shane, thank you again, and I will let you take it from here.
Okay. Thank you, Terry. I do want to thank Terry and the folks at the Astronomical League and Scott and the folks at Explore Scientific for inviting me back. I am a professional as well as an amateur astronomer. And so there's something that's very near and dear to my heart about coming and talking to people who are enthused about the science I do professionally, about the things that are very near and dear to my heart. So I do appreciate the invitation. It's great to be back. And so tonight, as Terry said, I'm going to tell you about black holes. So let me go ahead and share a few slides. I will say that, I got into this business, into the professional business, because I wanted to study black holes. So when I went to get my doctorate, it was because I wanted to study black holes. And I'm very fortunate that during my career, black holes have gone from being less well understood to being kind of mainstay pieces of modern astrophysics. And particularly with the advent of gravitational wave astronomy, which I talked about last time, but I'll also mention again here at the end, they are increasingly becoming objects that we can actually collect data on and observe and kind of learn about what their fundamental properties and what their nature is all about. Now, as you might imagine, I could talk about this every night for an hour for a year, and we would never get to all the things that we could talk about black holes. So what I want to do tonight, lots of you probably know some stuff about black holes. I'm going to go through some stuff that almost certainly you know or you've heard. Maybe I'll tell you some things that you don't know about. We'll talk a little bit about the history. But really what I want to do is lay some foundations for you to be able to go and do some more learning about this on your own. Okay. Now, invariably, you'll get to the end and, 2 weeks from now, long after this talk is done, you'll have some questions. I put my email address there. I do that at every public lecture I give. It's there for a reason. If you email me, I will do my best to help you find something to help you learn about whatever it is your question might have been. There's a link to my blog. I write a lot about black holes there, as you might imagine. I write a lot about astronomy. It is meant to be a public science blog. As I tell folks, it's written so my mom knows what I do. Okay, so hopefully you can find some stuff there that you may also enjoy. Okay, and there's my social media links as well. So if we're going to talk about black holes, we really have to start with this question. Especially among amateur astronomers, we've all kind of been exposed to the idea of black holes, and we probably have an idea in our head about what black holes are. But it's really important very often, I think, to very definitively say in clear language what we mean when we say this phrase, so we know what we're talking about. And one of the things that I often find is that people are bashful about the things that they know about black holes because they've learned them from science fiction or movies and not from professors and astronomy books, okay? But the truth is, even though our colleague Neil deGrasse Tyson roundly dislikes this movie, right? Lots of us learned about black holes from the very first time watching this movie. I certainly did, right? And one of the things that I love about science fiction in particular is for all the things that we as scientists complain about when we watch science fiction, or scientists like to complain about, very often there are kernels of truth. And those kernels of truth I find to be excellent places to have conversations. And people can say, I saw this in a movie. Is it real? Is it not real? And that provides an opportunity to talk about what we know or what we don't know, or what scientists think or don't think about all these exotic phenomena that fill the universe. And black holes are certainly one of them. And for everything that people dislike about this movie, I will say there are elements of the description of black holes in this movie that I think are spot on, and we should take at face value, because even today, decades after this movie was made, they are close to true, or at least close enough to true for folks like me and you to have an intelligent conversation about them. Okay, so as we go along, kind of keep all the stuff you know in your mind and think about the touchstones, the places where it overlays with the things I'm going to tell you, and ways that it made sense, or it got things right, in ways that it didn't make sense, or maybe movies got things wrong. Okay, so what is a black hole? I'm going to very simply define a black hole to be, and if we were all in the same room together, I'd let the audience do this for you, but I'm going to do it here. I'm going to make a very short and concise definition, okay? And the short and concise definition is not meant to capture all the properties and all the things that black holes can do and whatnot, right? But it's supposed to capture the essential thing that makes a black hole different from everything else in the universe, okay? And that essential thing is a black hole is an object whose gravity is so strong, not even light can escape, okay? And if we start from that definition, everything that we as astrophysicists think about black holes can follow, okay? Now, if you ask people who thought of this idea, you will often get the Albert Einstein's name coming up. But in fact, the idea of a black hole is far, far older than that. The very first person to propose the idea of a black hole was an Anglican priest named John Mitchell in 1783. So this is kind of 100-ish so years or so after Newton's publication of the Principia. And after in the Principia, Newton wrote down the very first mathematical description of gravity. And what Mitchell did was he asked, how strong would gravity have to be what kind of object could create gravity so strong that this definition I've written up here at the top of the slide is true, that light could not escape from it. Now, at that time, they had no preconceived notions about the speed of light other than it was fast. Okay, so he was just using the speed of light as some fast speed to try and compute what an object with enormous gravity had to look like. And what's remarkable about Mitchell's derivation is that it corresponds exactly today to what we call the Schwarzschild radius of a black hole. Okay, and there's deep reasons for that, because general relativity, the modern way we think about gravity, is not that different. In fact, it contains Newtonian gravity, the way Newton wrote down gravity in the Principia. So if Mitchell first thought of this, then what did Einstein add? Well, what Einstein added was actually special relativity, the idea that there's actually an ultimate speed limit in the universe. If you can't travel faster than the speed of light, and a black hole is an object whose gravity is so strong not even light can escape, then the thing Einstein added to this whole picture is that if you go into a black hole, you're never gonna get out. Okay, so that's the addition. And that's the thing that really, to our common sense, right, our everyday experience that we have with baseballs and Volkswagens and telescopes, right, that idea that you can't get out is the part that kind of is a stumbling block mentally very often, because we don't really experience such absolute statements in our everyday life. But the laws of physics, as we understand them, suggest that this is the case, okay? And indeed, everything that we've observed and discovered and know about black holes today points to the fact that this is still the defining character, okay? So, my goal here at the beginning for the kind of first, third of this talk is to convince you of this fact. Black holes are actually simple. Now, on the surface, that sounds like a bonkers thing to say, right? I went and got a doctorate studying black holes. How can this statement be true? But when I say this, I mean something very specific, okay? And you can understand this. If you just go down to your local supermarket or your local bookstore, you will find lots of magazines that look like this, okay? Car magazines that tell you all kinds of things about cars, okay? Everything you need to know. Tires, tires, engines, paint jobs, upholstery, horsepowers, all those things about cars, okay? And the reason there are so many magazines about cars is because cars are complicated. If I took a simple car like this Yugo right here, and I wanted to describe it, I would have to describe about 20,000 different parts. What their shape is, what they're made of, what kind of strain and force they can endure, how hot can they get, where do they go on the car, how do they interact and touch and attach to other parts. A car is a really complicated object, and that's why you see tons of magazines about cars. What you don't see at the bookstore are magazines like this, because contrary to the idea that cars are complicated, black holes are not. They're actually really simple. And using the same analogy that I used with the car, the reason we think black holes are simple is because it only takes 3 numbers to describe them. Okay, if I tell you these 3 numbers together with the laws of physics, that's the complicated part. But with these 3 numbers, you can discover, know, write down everything you need to know about a black hole. And those 3 numbers are the mass, the spin, and the electric charge. Mass is how much stuff is there. What's the stuff creating the gravity that the black hole exerts? Spin is how fast it goes around, like merry-go-rounds or tires or whatever. And electric charge is, the stuff you get out of the light socket when you stick a fork in it. Okay? So these 3 things are all properties that a black hole could have. And if I tell you these 3 numbers, I can use relativity, general relativity, to write down how a black hole interacts with the universe. Okay? So let's talk about the most important of those, okay, which is the mass. Okay, because the mass is the thing that defines the gravity of the black hole, really. Okay, and gravity is what the game is all about from our definition of black holes at the beginning. Okay, so black holes aren't solid objects, right? They're not like a star or a planet or Lego bricks or anything that you might be able to pick up in the normal world. They don't have surfaces. Okay, there is an outer layer to the black hole that we call the event horizon, but it's an invisible barrier that you can walk through and not even know you walk through it. Black holes aren't solid. And so if that's the case, the question becomes, what do I mean by mass? If it doesn't have a solid surface that I can lay my hands on and then grab and somehow measure, what do I mean by the amount of stuff in the black hole? Well, I often remind people that we talk about the mass of the sun all the time, but no person has ever gone up to the sun, grabbed it, and thrown it on a bathroom scale to measure its mass. Okay, it's far outside our ability to do that, but it's not practical in any sense of the word. Any astronomical object you can't measure the mass of, at least not in the conventional sense that you and I think of, putting things on bathroom scales. Okay, so how do we measure the mass of objects in outer space? Well, the typically way we do that is we use the laws of physics. I watch for things that I know of. In the case of the sun, maybe planets or maybe spaceships that we've sent to investigate the sun. We watch them orbit around the sun. And if I know the laws of physics, in particular Kepler's laws of orbital motion, I can just use a stopwatch to time how long it takes the object to complete its orbit and compute the required mass, which is equivalent to saying the required gravity, to make that object move in the orbit that I see. And so we can do the exact same thing with black holes. If I were to just replace the black hole for the sun in this image, then I can measure the mass of the black hole by looking at the orbits of things going around the black hole. Okay, and this lesson is central to the way we have to study black holes. The way we study black holes until very recently is we watch black holes doing things to other things in the universe. And we'll come back to that in a moment. Okay, but when we talk about mass, this is what we're talking about. How much mass would it take to create the orbits that we see around the black hole? Okay? Now, I can imagine these things all I want. John Mitchell originally wrote them down as an exercise in theoretical physics. Einstein, in general relativity as well. They wrote down the idea of black holes long before we had ever detected one in the universe. But if we want to be astronomers, right, if we don't want to just be mathematicians of physics, if we want to be observers of physics, then we have to look for these things out in the universe. And so the question becomes, what do we do? Well, there's a lot of different starting points you could take, but as astronomers, one of the things I often think the right place to start is to imagine, well, how is the universe going to make black holes? If these things do exist, and I can figure out some way by which the universe makes black holes, then that might tell me where to go look. Okay, now there's a whole bunch of this story I'm not going to tell you, but really, the thing that you need to do is you have to unleash tremendous amounts of energy in order to make an object's gravity so strong that it can become a black hole. And the only way that we really know how to do this, or traditionally know how to do this, is we can blow up stars. Now, as amateur astronomers, we are used to this. We've often go out and in our long lists of observing things that we get to see, there are things called supernova remnants. And so there's a long list of them I could show you, but a particular favorite one of mine is found off the wing of Cygnus. So if you go off the wing of Cygnus there's a naked eye star that the Telrad circle's on right there called 52 Cygni. And if you center on that star, you will see one side of what is known as the Cygnus loop. Okay, so the star in that image is this one right here. That's 52 Cygni up here. That's part of, this is sometimes called the Veil Nebula, the Eastern and Western Veil. This part is sometimes called the Witch's Broom, and the far side is sometimes called the Veil, but the whole complex is called the Veil Nebula. Now, this is the remains of a star that exploded. Estimates suggest it was about 10 to 20,000 years ago. And now all of these shattered remnants of what the star used to be are found in the night sky. But when the star explodes, it throws all of its stuff out into the universe, but its heart, its core, gets left behind. And that stellar skeleton is the thing that we're looking for, the beginning of our search for black holes. Now, we've looked for years and years and years for the stellar skeleton at the heart of the Cygnus Loop. We've never found it. There are other supernova remnants where we have. The Crab Nebula is probably the prime example there, but I like the Veil Nebula. That's why I showed you this one. So, okay. So what does that stellar core look like? So, if I ever give this talk locally to your club, I'll put your map of your local town here, okay? But I live in Chicago. Okay, and the stellar remnant of a supernova explosion takes one of two states. The less intense state is called a neutron star. When a star explodes, it throws off that remnant, that supernova remnant, and the core gets compressed down to something about the size of a city, typically about 20 kilometers across or so. So if I were to hang this object, this neutron star, as we call it, over the city of Chicago, you would see that it stretches from me up here at the Northwestern campus in Evanston, all the way down to the center of Chicago. Okay, this object is the size of a city, but it has 1.5 times the mass of the sun. Take everything in our solar system, the sun, all the planets, sweep it together, take another half a star, pile it in, and squeeze it down into the size of a city, and that thing you get is called a neutron star. It's so dense and exotic that normal atoms don't exist. Normal atoms break apart. All the protons and electrons combine to become neutrons, and so more or less, this whole thing is a gigantic pile of neutrons. We have a visualization of what it might look like hanging over the city of Chicago. So you can get a sense for, typical city skyline and this enormous but very small cosmological object hanging over the city. Of course, this couldn't really happen, right? Because if it did, you would see people and buses flying up from the streets up towards the star because its gravity is so intense. And that's really the reason I'm telling you about this before we talk about black holes, because the gravity of a neutron star is not the gravity of a black hole, but it is enormously intense, so intense as to be far outside any experience that we have here on Earth. If I could stand up on top of the Willis Tower or the Sears Tower, for those of you who are old enough there, okay, and reach up to that neutron star with a spoon and grab off a teaspoon-sized chunk of it, a sugar cube-sized chunk, okay, the mass of that little piece would be more than 3 times the mass of every man, woman, and child on the planet Earth. Okay, it's enormously dense. And as a consequence, the gravity is enormously strong. The gravity on the surface of the neutron star is 200 billion times more than the gravity you're feeling right now sitting in your chair. If you could take a stroll across the surface of a neutron star, and you had the sad misfortune of encountering a cliff just 1 millimeter high, and you fell off that cliff, by the time you reached the bottom, you would be traveling at 136,000 miles per hour. The gravity on the neutron star is intense, but it's still not the gravity of a black hole. If I want to make a black hole, my explosion, the supernova, needs to be a little bit stronger. The star has to be a little bit bigger before it blows up. But it will take a proto-neutron star, something that thinks maybe I want to be a neutron star, and squeeze it even harder. And it will shrink down until it is just about 3.5 miles across. And at that moment, everything that the star was collapses beyond that invisible barrier we mentioned, that event horizon, and disappears forever, hidden from view. But the gravity it leaves behind is this object that you and I call a black hole. An object whose gravity is so intense, not even light can get away. Which means if you walk across that event horizon barrier, you're never coming back out to tell us the story. Because nothing can travel faster than the speed of light. Okay? So that's how we make them. Okay? And once we realize, wow, nature could make these things, then we go looking for them. Okay? So my wife is also an astrophysicist, and so I asked her, I'm going to give this talk to the Astronomical League. I need to show them a picture of what a black hole looks like. Do you got one? And she's like, yeah, I absolutely got one, but I won't let you show it to them unless I get an image credit. I'm like, no problem, babe. You can have an image credit. So here's my wife's image of a black hole. Okay.
Wow.
Now, I can see Terry laughing, and I'm sure
that is dark.
Okay, but this is actually a serious picture, right? A black hole, by definition, that we agreed on at the beginning, is an object whose gravity is so strong, not even light can escape. But we're astronomers. We study the universe with telescopes. We gather light. So if we want to observe black holes, and we normally observe the universe with light, this causes a real problem for us because light can't get away from a black hole. So, since we can't get light from black holes, we do the thing we can. We look for black holes doing stuff to objects that we can see. Other stars, hot gas, right? Things orbiting it. All kinds of stuff fills the universe that we can see with our telescopes. And so if we can see them doing something exotic, then based on that exotic behavior, we can assure ourselves that black holes exist. Okay, and this is basically the process that has been going on my entire professional career as an astronomer, where I've lived through the transition from, okay, well, we could look for these things and maybe we'll see some exotic behaviors, to absolute confidence on the part of astronomers that these exist, because there's nothing else we can explain all the exotic phenomena in the universe we see. Okay, so let me give you an example of this. So many of you working through your Messier list, which we heard John talk about a little earlier. Okay, and so right in between Leo and Virgo and Coma is the Virgo cluster of galaxies. It's the nearest large cluster of galaxies to us. Those of you who are working through your Messier list, it's probably one of the first places you'll see multiple objects in the telescope field when you look. There are lots of faint smudges. You will get lost the whole time you're navigating through. But right in the center of the Virgo cluster is a monster. Okay, the monster is usually called Virgo A, or M87. It is a large elliptical galaxy. So elliptical galaxies are the piles that result from galaxies colliding and forming one larger galaxy. The kind of cool trivial pursuit fact I like about M87 is the Milky Way has like 150 globular clusters around it. M87 has 12,000 globular clusters around it. Okay, so it gives you a sense for the scale of the galaxy it is. Okay, but for a long, long time, people have stared at the core of M87, and it is known that there is a feature there. Okay, and that feature NASA has always pointed to. This is a picture from Hubble of this very long linear jet coming from the exact center of the galaxy. And if you saw the video that was playing at the beginning of the live stream, they were talking about these jets. These jets are a feature of active galaxies, as we call them. They are always associated with black holes, because black holes are the engines that drive the formation of the jet. And so, you know, in the kind of first decade after Hubble launched, this image here on the left, which you can get from the Hubble archive, is one that NASA would put up and say, smoking gun evidence for the existence of black holes. Okay, now famously, when I was first in amateur astronomy, a friend of mine, Mike Murray, who's the planetarium director at Delta College in Michigan, and Adam Block, who used to run the observing program at Kitt Peak, we took an image of the jet in M87, and you can see it right there with the 16-inch telescope. Okay, so this is in as much as John was encouraging us to not rely on technology all the time, this is something you can't see with your naked eye. But amateurs today have the same technology the pros have, to such an extent that we can actually see evidence for black holes from your own backyard. Okay, and I think that's kind of cool. So this jet is a consequence of material streaming down onto the black hole. The black hole in the center of the galaxy accumulates stuff around it. This is often called an accretion disk or an accretion torus that provides a supply of gas and dust and material that will slowly spiral onto the black hole. That material becomes very hot, emits X-rays and other wavelengths of light that we can see with our satellites. And then some of it gets stirred up into these jets. And that's a combination of conserving the quantities in physics that must be conserved, energy, angular momentum, things like that, if you remember your physics classes, but also the magnetic fields and the energy dynamics of what's going on down there in the core. But it's the black hole that ultimately provides the energy to push that jet just light years and light years out into space. And we see these in many different galaxies. They're very common, and they all point to black holes. Okay? Now, those of you who pay attention to the news and listen about black holes all the time, you will know that the big news of late is we've finally taken a picture of a black hole, as the story goes. Okay, so this is the picture of M87 again, this case, taken by the Event Horizon Telescope collaboration. And so what you see here is this very bright donut. And you should kind of keep watching the news, because our colleagues who work on this are constantly getting better data and doing better image processing, so these images get better and better with time. But this donut here is not actually the black hole. It's, as we say, the shadow of the black hole. The shadow of the actual black hole is about, where I'm circling my mouse there, 2/3 the size of this or something like that. But what you're seeing is the black hole bending light around it from the accretion and the gas and the hot material that's around it, and creating this donut shape. And precisely mapping out this donut shape, the sizes and the places where it's bright and where it's dim, are a way of mapping out the gravity of the object creating this image. And it precisely matches the gravity we expect for these objects that we call black holes. So this is almost certainly the best picture we're ever going to be able to get of a black hole without actually flying out to one and, taking a picture from up close. Okay. But from our vantage point here on Earth, this is the kind of image that we're always going to be able to get. Okay. And it's a tremendous and a remarkable technical achievement. And you should be blown away by what our colleagues on this project have done. They've released a second picture. I probably should have put it in the talk. I'm sorry I didn't. Of Sagittarius A star, which is the black hole at the center of our own Milky Way. So in terms of size on the sky, M87 and Sagittarius A star are the two largest black holes, which is why they're the ones they're taking these pictures of. So, okay. So observing is getting easier. We know what to do. We know how to look for them. We got many, many examples of black holes of all kinds of different sizes now. And so the other part of that, though, when you're looking for black holes doing exotic things to objects we can see, is understanding what black holes actually do to the world around them. Okay, so I want to kind of ask the question and kind of walk through very briefly what happens if you get too close to a black hole, because that's what's going on in these pictures. Some astrophysical object, maybe it's gas, it could be stars, it could be all kinds of things, get too close to black holes, and the black holes do bad things to them. Okay, and so what happens if you get too close? So let's not talk about exotic stars that we don't have experience with, right? Some of you may, some of us do, but let's talk about some explorers that we can all appreciate, okay? So I want to send these two explorers into a black hole, okay? Now, when we did this, we realized I should have been Starfleet Ernie that year, but we'll leave that for some other time. So, okay, so these are our two explorers we're going to drop into the black hole. Now, the thing I want to do is I want to look at the force, the gravitational force that an explorer experiences as they jump into the black hole. And I've asked Bert here to jump in feet first. What happens is the gravity of the black hole, the strength of the gravity depends on how far away you are. So if you're close, the gravity is strong, represented by this big arrow pulling you towards the black hole. And farther away, the gravity is weak, represented by an arrow that's smaller, but still pointing towards the black hole. Now, we're used to this, right? You and I experience plenty of gravity here on the surface of the Earth, but if we go out into orbit, then we don't feel the same gravitational pull that we feel right here on the surface. Okay, so gravity does get weaker with distance. The difference between something like the Earth and a black hole is this change in gravity happens over very short distances. In fact, it can happen over the scale of Bert right here. If Bert jumps into the black hole feet first, it pulls very, very strongly on Bert's feet and less strongly on Bert's head. And so the effect of the black hole is to try and stretch Bert apart, to pull them apart. There's a technical name for this. We owe it to Stephen Hawking. If you go look up this on Wikipedia, it will attribute it to Stephen. He's the one who made it. We call this spaghettification, okay? If you want to be all technical and impress your parents with cool physics words you learned on YouTube tonight, what a physicist would call this is a tidal force, okay? A difference in force between 2 points on an object. Okay, it's the same force the moon exerts on the Earth to produce the tides. That's why we call them tidal forces. Okay, but with black holes, we often use this term spaghettification precisely because it is so extreme. Okay, and you can't tell it because Bert's long-headed to start with, right? Bert's kind of stretched out. But if we threw our captain in there as well, they would definitely be getting spaghettified. The black hole would be pulling on the captain's foot, trying to stretch the captain out into a long, thin piece of human spaghetti. Okay. Now, the thing about this when you first hear it is it sounds exotic, right? But in fact, we see this happen in astronomy all the time. One of the kind of current hot fields in observational astronomy is looking for tidal disruption events. Okay, so this is a simulation of a gas blob that we had seen approaching Sagittarius star. You can see the years ticking by down there that we did a simulation of. And when it restarts, if you watch, you'll see the blob was initially very compact. And then as it went around the black hole, the parts of the black hole that were closest to the blob pulled really strongly towards the black hole. And then everything else kind of kept going and everything stretched out into these long streamers that we call tidal tails. Okay. The material keeps streaming onto the black hole. That's what produces all that bright X-ray light and radiation that we look for in our telescopes. But the object itself is eventually disrupted and destroyed. Okay, this is what we call a tidal disruption. Okay, it actually happens around black holes. We've seen events that we think are tidal disruption events, but it also happens right here in our solar system. Okay, so I got into amateur astronomy because I wanted to build a telescope to watch comet Shoemaker-Levy 9, and David was here with us a little while ago, right? Crash into Jupiter. In 1992, this comet, Shoemaker-Levy 9, came too close to Jupiter, and the side of the comet that was close to Jupiter got pulled on more strongly than the side of the comet that was far away, and it broke it apart into this long string of mini comets that we call the string of pearls, famously, if you go read about this, okay? And so they were trapped by Jupiter's gravity, and just like the black hole absorbs gas, the comet eventually fell onto Jupiter. And when they did, they produce these spectacular explosion sites with these black scars on the surface of Jupiter that we could see with our telescopes, with our amateur telescopes from here on Earth. Okay, so I particularly like this because this is what got me into amateur astronomy, but it's kind of closely related to something that I study every day. Okay, so tidal disruption events are not exotic. They happen here on Earth. They happen all the time. It's just black holes take it to the max. Okay. Now, there are other ways. Let's go back to that idea about orbits. There are other ways to see black holes, and that is to watch individual stars. And this is the way that we actually mask black holes. So the closest, sorry, this is not true anymore. Traditionally, the closest black hole candidate to Earth is Cygnus X1. It's just under 6,000 light years away. This is a finder chart. You can actually see the star that's the companion of the black hole in your telescope. You can kind of star hop through there if you want to. But what is going on is there is a blue supergiant star that is in about a 5.5-day orbit around an object that we can't see. Okay, we could see the star wobble, but when we first started doing X-ray astronomy in space, this is the brightest X-ray source in Cygnus, and it's because the wind from the blue supergiant is captured by the black hole's gravity. All of that gas in the wind spirals down onto the black hole. It gets very hot. It emits X-rays, and so we can see it as an X-ray source in the sky. Okay, based on the size of the blue supergiant star, based on the X-ray emission, based on the period of the orbit, this black hole is about 20 times the mass of the sun. Okay. Now, I said this used to be the closest candidate to Earth. Some of you may be aware of the Gaia experiment, which is measuring the distances to something like 1 billion stars in the Milky Way. And so there are like constantly papers popping up. Oh, new system discovered by Gaia. And one of those systems I recollect right now is a black hole binary system that's closer than this. And I just don't have the information off the top of my head. But traditionally, this has been the closest black hole to Earth. Okay. So this is all kind of classic astronomy. This is the stuff that's been bubbling around now for the entire time that I've been a professional astronomer. But as I told you at the beginning, right, I went to graduate school to study black holes, and I fell into this game called gravitational wave astronomy, which is about looking at the universe not with light, but with gravity itself. And that makes it an ideal tool for studying black holes because black holes aren't made of anything. Black holes are made of pure gravity. So when I started in this game, we could only do these things theoretically. This is a theoretical simulation done by my colleagues at Goddard about how two black holes orbiting each other bend space-time. It creates distortions in the gravity, which then ripple out into the universe in waves that we call gravitational waves. And you can see them going out in every direction from this simulated black hole merger. This simulation I like to show, you often see lots of different simulations that kind of look like ripples on a pond, but I like this one because it shows that the gravitational waves go in every direction in much the same way that light from a star goes in every direction. And that's useful if you're an astronomer because it means it doesn't matter where you live in the universe. You'll be able to see the waves, the gravitational waves in this case, from this object, okay? Now, Einstein famously predicted that these gravitational waves would exist in 1916, okay? And he spent the rest of his life wondering whether or not they existed or not. And he would constantly oscillate back and forth between they do exist, they don't exist, they do exist, they don't exist. And it wasn't just Einstein, right? Einstein, the entire physics community was confused. And the reason for that is that this is a prediction from general relativity, and it says something about the universe. It's the phenomena in the universe that our senses, our bodies, are not designed to detect. None of us have a gravitational wave detector in our elbow, right? It's not like our eyes, right? Telescopes are basically bionic eyeballs, but none of us have gravitational wave detectors. And so it took physicists 50 years to convince ourselves, oh, these things are real, and this is how we could build an experiment to do it. Okay. Now, Einstein himself had imagined trying to build experiments to measure this, but he famously thought it would never be able to be done because he thought the effects, he's correct, the effects were enormously tiny, right? He was imagining, could I build something in the laboratory that would generate gravitational waves and let me measure them? And he's like, nope, it's too small. There's no way this will ever work. Okay. But you and I live in the future. Okay. And we have technology and understandings of the laws of physics and capabilities that Einstein didn't have. He passed away in 1955. In about 1957, we finally figured out what we ought to be doing. And it took us all the way until the early 2000s to build an observatory, which today we call LIGO. Okay, our colleagues in Europe have one called Virgo. Our colleagues in Japan have one called Kagra. But LIGO discovered the first gravitational waves finally in 2015. That event is called GW, Gravitational Wave 15, 2015, 09, September 14th. Okay, so on September the 14th, I had just moved into my house. I got an email from Vicky, my director of the center here, that said, uh-oh, I think we saw one. And what we had observed were gravitational waves, nothing else, no light, no other signal, gravitational waves in LIGO from two black holes spiraling around each other and merging to form a single bigger black hole. This is 400 megaparsecs away, 1.3 billion light years away. And that gravitational signal has propagated across the universe until it washed across Earth on September 14th, 2015. Okay. The final black hole that you see there is about 227 miles in diameter. So if we were to lay it down on the state of Illinois, it would stretch all the way from Indiana to the Iowa border. Okay. At the time we discovered this, if you had asked me on September 13th, we would have told you we didn't know black holes this size existed. We would have told you the largest black holes would be about 10 or 15 solar masses. But what we saw were two black holes, each roughly 30 solar masses, crashing together and leaving behind something that was 62 times the mass of the sun. This single event completely transformed our understanding of black holes in the universe. Sorry, it transformed our confusion of black holes in the universe because we still don't understand where these things come from, but we know they're there. And today, now almost a decade, not quite a decade later, there are nearly 100 such mergers that we have seen. So you can get this plot on our website at Sierra. There's a little tool that lets you, an interactive tool that will let you play around with it if you want to. But all of these blue black holes are mergers of black holes that LIGO has seen. The red ones are everything that we knew about before LIGO's first detection. Okay, so in less than a decade, we have increased the number of known black holes by something like a factor of 5. Okay, so you and I are living in an era where we are slowly becoming inundated by so much information about black holes that we will be able to answer almost any question we have about them. Because finally, it's more than just a game on a piece of paper, writing out some math. Science is always this interplay between observations and theory. Theory describes what we think's going on. The observations are the proof that the universe is doing that. And for 100 years or more, we've been thinking about black holes from that theory side. But today, in my career as an astronomer, and especially in the last decade, we finally have data, observations that are shaping what we think and what we know about these really exotic objects. It's going to get even better because I work on this mission that Terry mentioned called LISA. We will launch in the early 2030s, and we will see black holes in the centers of galaxies. Okay, so questions exist still of where do black holes like that one we see in M87 come from? And one of the only ways we can imagine they grow is crashing together with other black holes. Okay, and so LISA, this is one of the prime things that it should be able to observe. So in 10 years, when I come back to do an AL lecture live, I'll have data from Lisa to tell you all about this. Okay? So that's all I'm going to say. I always like to leave you with things to read and learn on your own. This book here by Marcia Bartusiak, some of you may have read Marcia's book. She's an excellent science writer. This one won a science writing award. It's called Einstein's Unfinished Symphony. It's about the construction of LIGO and the quest for gravitational waves. The book does come in 2 editions. If you get the second edition, there's an additional bit in there about the first detection that I just told you about. So it's an excellent book. If you kind of want to, melt your brain and understand a little bit about general relativity and black holes and all the weird stuff that happens, this book by Kip is probably the best one. It's very complete. It also won a science writing award, and it kind of has a whole bunch of this kind of cool bending space-time stuff in it that you may enjoy. If you have a little bit of technical expertise, that is, you're not afraid of algebra, this is a book that some people use as a textbook, but it's called Exploring Black Holes by Ed Taylor and John Wheeler. And it kind of goes through all the technical details of tidal forces and stretching space and stretching time and how GPS works and all kinds of cool stuff, which is related to black holes. And so this is good for those of you who just want to, practice your algebra skills. Okay. Here's a link to my blog again, and then here's a link to a set of kind of 12 posts that I wrote for the 100-year anniversary of GR, which kind of tries to teach you about GR from the ground up without using a whole bunch of math. So you may find that enjoyable. It gets to black holes somewhere in the middle there and gravitational waves near the end. Okay, so I am going to end right there and say thank you for your time, and I will turn it back over to Terry.
Thank you, Shane. That was amazing. That you have taken a subject that honestly I didn't know a lot about, and you made it understandable.
That was our goal.
You did an amazing job. Thank you so much.
No problem.
That was incredible. Are there any questions, or is there anything that anyone else would like to ask?
Yeah, I just
your brain's melting right now, so
it's fried right now. But thinking of a black hole as just pure gravity.
Yeah, right.
Nothing else, just pure gravity. You've got stuff that's being captured by it. What's happening to, what would happen to a planet or a star or something gets sucked into the black hole? Does it just convert to pure gravity, or that's happens to everything else?
Right, that's a great question. So the thing that happens as you get closer and closer to a black hole is that tidal stretching gets stronger and stronger. Okay, now perhaps counterintuitively, if the black hole's bigger, if it's like the size of the black hole in M87, you can go all the way up to the edge of the black hole and not become spaghettified. The forces will not be so strong that you feel bad about it, and you can cross over the event horizon into the inside.
Okay.
But at the point you do that, the gravity is going to constantly pull you towards the source of the black hole gravity, which at the center of the black hole is an object that we call the singularity.
Okay.
The singularity, many of you have heard this term. It's an object whose gravity, which is not precisely described by the laws of physics. If I look at the predictions for the gravitational field at that point, it becomes infinite, which we believe is an impossibility, right? Infinity is a mathematical idea. We don't think it's a physics idea. And so what we usually say is the laws of physics break down near the singularity. But all the way up to the point where the laws of physics break down, those tidal forces are getting stronger and stronger and stronger and stronger. And so once you're inside the black hole, even if you survive through the event horizon, as you get closer to the singularity, you will get spaghettified. Okay. And then that singularity, it's a source of infinitely strong gravity. It's going to pull all the material into it. And at that point, we don't know what happens. Right? It gets compressed into something that's infinitely dense and infinitely small, and those concepts don't mean anything. Okay.
Right.
And there's a great book by Lenny Susskind, I think, called The Black Hole Wars. Okay. And this is all about what goes on inside the black hole. What happens to, right? If I throw information into the black hole, a person, a book, right? The quantum states of all the atoms that fall into it. What does the black hole do with that information? This is a huge issue in physics. Is it lost or is it preserved somehow? But it's all related to the fact that we don't know what's going on with that singularity.
I see.
Yeah.
Okay. Or I don't see.
So the inside, right? Yeah. Anyone who says they see is completely fooling you, right? So
right.
But the inside of the black hole is empty space as well. That's what we mean when we say the black hole is pure gravity. It's just pulling everything towards that singularity. The singularity is the only thing, and we don't even know what it is.
Shane, that is fairly well accepted now, isn't it? The theories that you were just describing tonight.
Yeah, so especially with the gravitational wave detections, but especially with the Event Horizon Telescope pictures, with all the kind of probing of what's going on close to black holes with tidal disruption events, we take all of those observations. This is the data side of astronomy, right? We say these are our observations. This is what nature's doing. We can't argue with it. Right? Maybe the observations are great, maybe they're not, but the point is they tell us this is what the universe is doing. And if we compare that to the predictions of general relativity, which is what we understand gravity, the correct description of gravity to be, we have not seen any anomalies between the two. Okay? So as physicists, as astronomers, what we say is the data, the observations, and the mathematics are in agreement. But we keep looking. We keep trying to probe closer to the black hole. We keep looking for new black holes. We keep looking for new events because we know, and the history of physics is replete with this kind of case. We know that as we get better with our observations, we get more precise, we get to smaller scales. Eventually, the way we currently describe physics isn't going to be good enough anymore. And there will be some new additional bit that we have to add on. And the frontiers in gravity are something called quantum gravity. How does gravity behave on the most microscopic of scales? And whether or not we can get there with astrophysics, or we need something like particle physics or something string theory, something different, that remains to be decided. But this is the frontier right now, right?
Thank you. Well done.
Yeah.
You mentioned that there was a second picture of Sag A. Is that something that is online somewhere that?
Yeah, here, let me see if I can pull it up in a web browser while we're here.
Okay.
So Event Horizon Telescopes, SGR A star. Yeah, rock and roll. Okay, so in fact, here, let me pull up this image because this is the two of them together.
Okay.
And let me put it in a window all by itself so I can share the window. Waiting for it to load here. Okay, so this is the two Event Horizon Telescopes pictures side by side. So this is the one I showed you of M87 on the right, and this is the Sag A star one. So the Sagittarius A star, Sagittarius A is this complex right in the Milky Way. So if you look at the teapot of Sagittarius, you kind of go up where the steam coming out of the spout would be. That's the direction of the center of the galaxy. So Sag A is the complex there, and Sag A star is a compact radio source at the location of the black hole. So we typically call the black hole Sagittarius A star because we think it's the source of the radio emission. But this is the ring around Sagittarius A star, and it's different than the ring around M87. But that's because the gas is distributed differently. We're looking at the black hole at a slightly different angle. Okay, but you can see they're roughly the same size. They have the same kinds of features. And to Carroll's comment a moment ago, right? This is our data. So we use this and we compare this against simulations of what does light around the black hole do, and how does that arrive at our telescopes, and what kind of image would it look like? And this is in agreement.
So these are the two largest black holes that we know of, correct?
Yeah, well, so they're not the largest black holes. They're the black holes that have the largest size on the sky, right? So we're talking about angular diameter,
Okay.
right?
Okay.
Because it's just like anything, right? The moon's a certain size because it's at a certain distance from us. But if
Right.
we pushed it farther from Earth, it'd get smaller. If we brought it closer, it'd get bigger.
Right.
The black holes are the same way. So these two black holes, based on their size, but their distance from Earth, they have the biggest apparent size in the sky.
Mhm.
Okay.
So that's why they were the targets. There are other
Yeah.
black holes we could try and image, but they won't make as big a shadow image as these make because they're smaller in apparent size.
When you
And you
say,
mentioned-
go ahead, Terry. Go ahead.
You mentioned the black part of the donut there.
Mhm.
The actual black hole is not as big as the dark center, correct?
Yeah, right, exactly.
Okay.
Yeah, and that has to do with the path that light takes as it goes around the black hole. Because if it's trying to go around the black hole by just skimming over the surface of the black hole, it usually doesn't have enough oomph to get away from the gravity of the black hole and falls in, right? But as you get farther from the black hole, the gravity gets a little weaker, and the photons can eventually wind their way out. So the size of this donut is actually an indicator of the fact that there's a black hole in there, right?
Okay.
In these images, Shane, it seems that you know a lot more than I do, or could even find out.
Not as much as my EHT friends, but I'll tell you what I know about that.
But I'm looking at the images, and of course, we see these brighter areas here. The Sagittarius got 3 bright areas in that ring, but I also notice a fainter, background.
This stuff.
Detail. Yeah, these things.
Right. Yeah.
Are these like jets? Are they? Is it material of some sort?
Yeah, so it is absolutely material, right? Because what you're looking at here, this is all done with radio telescopes, right?
Okay.
So radio emission comes from gas at a certain temperature, and the intensity of the emission is how much gas at that temperature where it is. And so,
Okay.
as you go out this way, this gets fainter, so there's less and less gas. But the fact that you're seeing radio emission here means there's something there producing that signature that you're seeing in your telescope. It's emitting the light. And if you look on bigger scales, you can. So if you go Google images about the Sagittarius complex, there is enormous molecular clouds of gas and dust down in this region, right? There's lots and lots of stuff, both close to and far from the black hole. And so this is part of that extended emission, but this is the stuff that's closest to the black hole, right? Because the black hole's this big, so you're only 5 or 6 black hole radii away when I'm talking about this, right? The scales that we're used to looking at stuff on the centers of galaxies is kind of much light days across, right?
Sure.
But here, this is stuff that's really close, and it's emission, so it's gas of some sort.
Huh. Okay. It's very, very interesting. And
It's
your
cool
talk
stuff,
was wonderful. And the audience that responded, they don't have questions, but I think that they really enjoyed. They said we're all. I asked Ronald Green, watching on Facebook, if he had any questions at all. He says not now, but it's a great talk. So.
Okay. Well, I'm glad everyone enjoyed it, and I appreciate the invitation.
Yeah.
Hey, you are welcome anytime. We appreciate the talk,
We'll
and that
do
was
it again.
amazing.
We have a date in 10 years after Lisa flies, right?
No, we're going to have one before that.
Oh, okay, fair enough.
All right. Thank you so much.
Okay.
That really was incredible. So,
Thanks,
all
Alan.
right. I am going to go back to the questions and give the answers to the questions that we've. Okay. I am not able to. Let's see if I can share this way. Here we go. There we go. Let's see. I think that's it.
You're sharing?
All right. There we go. Which screen I need to look at. Okay. All right. So here we go. The answers to the questions. First question was, while driving on the moon, the fender on the rover was damaged. What did the Apollo 17 crew use to fix the fender? They used 4 maps and duct tape. Harrison Schmidt was at Alcon this year talking about that. It was amazing to listen to the stories. So yeah, that was really cool. The winner is Barbara Brown.
All
Next
right.
Next question. On December 7th, part of the US will see this occultation of what planet? And that's going to be Mars, being occultated by the moon. And the winner is Jess Myers. And the last question. On November 16th, 2022, Mars will be in what constellation? It will be in Taurus, but it's really cool because it's going to be centered between the horns of Taurus. So I think that's pretty cool too. So our winner is Marilyn Wright. And we'd like to thank all the people that answered the questions and thank everybody for tuning in. And I would like to thank everybody that has been on the show tonight. We had David Levy, Carroll Iorg. He is the Astronomical League president. We call him the leader of the pack. John Goss, League media officer. Scott, we couldn't do this without you. Thank you so much for everything you do. You are greatly appreciated.
My honor and pleasure. Thank you.
Hey, we are so honored to have you. So, and Shane Larson. Oh my gosh, Shane. That was a fantastic talk. I really enjoyed that, as I know many more did. Thank you so much for being on and everything that you have taught us. I will definitely be in touch with you next year. We'll see if we can't get another date put together.
We're on it.
That sounds great. And thank you to everyone that is watching. And we wish you all a happy Thanksgiving. And we're going to let you know we will be back Friday, December 16th. What we are going to do is bring on all of the Astronomical League officers, so we can tell you what the year has been like and kind of wrap up 2022 and welcome 2023. And our speaker, our keynote for December 16th will be Bob King. And he's going to talk about the sun, equipment, a lot of things about the sun. And we'll all start talking about the solar eclipses coming up. There's one in 2023 for an annular, and 2024, we've got the big one coming across the US. That's going to be a big one for all of us. So thank you all for that and for being with us. And please join us next month. We really appreciate it. And I think that will probably wrap us up for tonight, unless somebody else has anything they would like to say.
People are, Harold Locke says, thanks for a great show. And Mike Moderkin, I think is how it's pronounced, or Martison, said, will this be available on YouTube? If you're watching on YouTube right now, I can see you're on Facebook, but yes, it will be available on YouTube. You can go to the Explore Scientific official YouTube page and find it there. Of course, you can watch it again on the Astronomical League Facebook page. I've put a link in the post of this program, and so it's going to be out there in perpetuity unless a black hole comes and swallows it up. So.
And then we're all doomed anyways. So.
And then it might be preserved forever and ever. I don't know.
Yeah. Who knows what happens after it goes in? That's right.
And Mike is from the
Omaha
Mike is from the Omaha Astronomical Society. So
That's great. That's great. Okay, so Stephanie Bain is watching. Ronald Green. These are just people that chimed in. A lot of people watch without really chatting with us, but. It's great to have you watching. Mike Peoples, who was talking to us recently about the Northeast Astronomy Forum and the imaging conference that's coming up. Okay, Connor Bradley was watching. He had questions about the moon and the trails from the Tycho crater on the moon. So I was able to answer that for him. I think that's going to do it for tonight. So thank you very much. And Terry, thank you.
Hey, thank you, Scott.
All right.
So
Okay.
this is number 22, correct?
Number 22.
That's right.
Can you
Incredible.
believe it?
That's a big pile of them.
Yeah,
That's
it
right.
is.
That's right.
That's
Yeah, I'll have to add up all the hours and all the, all the views and everything else. So we'll get to that, Terry. Thank you again
Okay.
to everybody that's watching and will watch this program. If you want to learn more about black holes, you probably need to watch this program about 10 times. Okay.
Yeah.
Okay.
or come study them with me. Go back to college.
That's right. And then ask the questions from Dr. Larson. Okay.
Yes.
So that's great. Keep looking up, and we'll be back again with another Astronomical League Live.
See you December 16th. Thank
Take
you.
care, everybody. Good night.
Good night.
Okay. Good night. There is no audio with this, but I thought it was a great visualization of gamma ray burster 221009A, where they think a new black hole formed in that heart of a collapsing star.